the problem statement says, in this figure here, in this here figure, a box of Cheerios and a box of Wheaties are accelerated across a horizontal surface by a horizontal force. Okay, applied to the Cheerios box. And then we do have friction. We have friction on the Cheerios, and we have friction acting on the Wheaties. Okay. If F is 12.5 newtons, what's the magnitude of the force on the Wheaties box from the Cheerios box? So let me state this right now. Let's always use, I think I've said this before, but let's always use the F on what from what convention. The F on what from what convention. On what from what. So what they're asking for here, they're saying, what is the magnitude on the Wheaties box from the Cheerios box? So they're actually saying, what is the force, the magnitude of the force on the Wheaties? So W comes first from the Cheerios. C comes second. So I would read this right here. What is the force acting on the Wheaties from the Cheerios? That's because, again, of this F on what from what convention. All right, so let's do free body diagram. Let's do the whole force analysis. So let me get a different, no, that's fine. Here's my free body diagram. It all starts with the free body diagram. There's my floor. Here's my Cheerios box right here. Let me get a different color. Cheerios box. That's my Cheerios box. So let's talk about the forces acting on the Cheerios box. I have the weight force acting down. So this is going straight down from the center of mass. And we can label that mass of the Cheerios box times G. What else? Oh, I have that externally applied force, that F force. So I will add that. This is my externally applied force, F. So this is F. What else? Or is that it? Well, no, there's the normal force. And the normal force technically acts on the shared contact surface. Here's the shared contact surface between the Cheerios and the floor. So my normal force is going to be perpendicular to that. So I'll draw that like this. Okay. What else is that? No, that's not it. Because I actually have a reaction force. I have a force that looks like this. Ready, set. I guess like ready here. What is this force? This is the force acting on the Cheerios from the Wheaties. All right, so this is kind of maybe new. This is a Newton's third law reaction. Remember what Newton's third law says. Newton's third law, N3L. Newton's third law basically says this: forces always occur in equal and opposite pairs. Forces, you'll never be able to find an exception to that. It's kind of fun to think about it. Forces always occur in equal and opposite pairs, which makes life easier. I mean, that's great insight to have as a scientist or an engineer or a technologist. It's great to know how the universe works. I mean, how many jobs out there are disconnected from the universe? My wife works for Ford Credit, and she works on credit card applications. And that's completely devoid of any sense of reality in terms of physical reality. All right. So there you have it. That's the free body diagram for my Cheerios. I'll label that right here. This is the mass of my Cheerios box. I'm going to do the same thing now for my Wheaties. And I think I'll move this over here. I'll use the same. All right. So here's the Wheaties. Wheaties is green. So I'll just draw it like this. I'm not going to draw them side by side. I'm going to draw them offset of it just so we can see things maybe a little bit clearer. Okay. So there's my Wheaties force. My Wheaties object. Okay. Just doing some housekeeping here. What's my free body diagram? So I'm going to do the weight force acting on the Wheaties center of mass. This is mass of the Wheaties times G. I have another normal force, so I better worry about subscripts since I have two of them. This is the normal force acting on the Wheaties. So I better call this F subscript N Wheaties, and this is F subscript N C for Cheerios. Okay, and this is mass of the Wheaties. What else do I have? Oh, and you know what? I actually forgot a force for the Cheerios. I forgot friction force. So let me add that right now. Here's the friction force. Ready, set, go. I know it's going in that direction. So this is the friction force acting on the Cheerios. Because the boxes are moving. How do I know they're moving? Because the problem says they are accelerated across the horizontal surface. So I know for a fact that the boxes are moving. If they are moving, there is for sure a kinetic friction force, because kinetic friction will always try to fight velocity. So this is FKW. And I'm going to indicate, because what I just said is worth pointing out. The velocity of the Cheerios is in that direction. The velocity of the Wheaties is also in this direction. Again, I'm showing them separated, even though in reality, this is what's really happening. In reality, the two boxes are side by side. What else for the Wheaties? Oh, here's something interesting. I actually have my Newton's third law, opposite and equal reaction pair right here. I got to move this, I guess. Let me just shrink. One more force acting on the Wheaties. And it's technically a normal force. And it's basically the force exerted on the Wheaties by the Cheerios. And I'm going to draw that. And when I draw it, it looks like this. Ready, set, go. And label it. So this is the force on what? It's F on what? On the Wheaties. From what? From the Cheerios. That's my dollar sign. So finally, at long last, I see my dollar sign. There it is. And then a very important note. I guess I'll get started here. Step number one. I'll go over here. Step number one. Aha. Newton's third law says all forces occur in opposite and equal pairs, as opposite and equal pairs. Newton's third law says that whatever FCW is, that's going to be the same as FWC. So that's good to know, especially since this is my dollar sign. I need to find the force acting on the Wheaties from the Cheerios. So off and running. My free body diagram is done. FBD is done. I don't need to do anything fancy with the coordinate system other than address it. Here's my coordinate system. Just standard coordinate system. I don't need to rotate, so I'll just draw it right here. For both objects, this is going to be plus X and this is going to be plus Y for both objects. Okay. Done with the coordinate system. I don't need to decompose because I don't have any two-dimensional vectors. And now it's time for the X force inventory and or the Y force inventory. Here goes number 2. I guess I'm going to start on the Wheaties. Look at the Wheaties box because that's where my $sign lives. So if I look at the Wheaties, this is what I have. I have plus FWC, that's going rightward, right there you can see, minus FKW, minus the kinetic friction force acting on the Wheaties. And I guess that's it, isn't it? Okay, and it equals mass of the Wheaties times A sub X. Because I should have started off a little bit sloppy here. I should have started this off with great care that says the sum of all X dimension forces. Okay. So let's say something about acceleration. We need to make an acceleration statement. And here's what I'm going to say. I'm going to say whatever the acceleration is on the Cheerios, A subscript C, that's going to be the same as the acceleration acting on the Wheaties. And so let's just call that A. And because mass of the Wheaties, or the Cheerios box and Wheaties box move together because they're just right next to each other. And if you push on them, they're going to remain right next to each other. So that's an important statement. All right. Let's number 4 then. What do I do? Isolate FWC because that is my $sign. FWC, the force on the Wheaties from the Cheerios, is the $sign. So I have FWC equals mass of the Wheaties, acceleration X plus FKW. And let's see, what do I know? Am I done? Could I possibly be done? I know FKW. That is the kinetic friction force acting on the Wheaties. And that for me, what is the magnitude? For me, the magnitude of the frictional force acting on the Wheaties is 4.6. So I know this number. This equals 4.6 newtons. So I know that. Do I know mass of the Wheaties? I do. Mass of the Wheaties is 2.9 equals 2.9 kg. Okay, the only problem is I don't know acceleration. So trouble in paradise, but not to worry. Now what? Number 5, how do I find X? How can I find A sub X, I should say. How can I find A sub X? And you might be thinking, well, do a Y force inventory. Maybe, but I can't see. Well, maybe I will have to do the Y force inventory, but I remember this is the tactic we used in chapter 5. We basically treated both of these boxes as a single object. So I'll just draw one box. This one box here can be considered to be a single object. So I know the mass of this box. The mass of this box is the mass of the Cheerios plus the mass of the Wheaties. Yes, I know that. What are the forces acting on it? I have the weight force acting down. So this would be mass of the Cheerios plus mass of the Wheaties times G, because weight is mg. I know the normal force is going up like that. So this is the normal force, F sub n. I have this externally applied force on the Cheerios, and I think, oh, and then I have my two friction forces. I have the friction force acting on the Cheerios, FKC, and then I also have the friction force acting on the Wheaties. So those two friction forces, they're still there, FK Wheaties. So now that I'm considering this as a single system, these two boxes are staying together. So I'm just going to consider them to be a single object. Let's do an X-force inventory. Let's do an X-force inventory on MC plus MW, the two boxes together. When I do that, I get sum of all the X dimension forces. And again, I remember this tactic from chapter 5. So that's where it came from. All right, so I have minus FKC, the kinetic friction of the Cheerios. Yes. Minus FKW, the kinetic friction force acting on the Wheaties. And I guess that's it. Plus F equals mass times acceleration. Say something about acceleration. And I can say something about acceleration. I can repeat myself because I said previously the acceleration of the Cheerios is the same as the acceleration of the Wheaties, and let's just call that A. So maybe I better say, in this case, let me fix this. Here's my acceleration, A sub X. In this case, equals A sub C equals A sub W. So that's a little bit better. And right now I can find this, I think. Solve for A. So from step 7, here's what I get for A. A equals minus FKC. And I know numerically what that is. Minus FKW. I know that numerical value plus F. I know that numerical value divided by M. And I might need to update this. This is the mass of the Cheerios plus mass of the Wheaties. And let me just go back and repair this a little bit to be a little more tight. F equals MA. And more specifically, the mass is mass of the Cheerios plus mass of the Wheaties times A sub X. Okay, so hopefully you can see clearly how number 7 comes, how number 9 comes from number 7. I guess this is all good. Okay, so you're going to get a value for acceleration, and then now solve number 4 and be done with it. Now that I have acceleration, and I have numbers on everything in step 9. Okay, and that's my answer.